Hello, my name is Shane Finney, and this is Lab 3 of Physics 2211, the Black Hole Lab. Alright, so the purpose of this lab is to illustrate Newton's second law and the universal gravitational force with a theoretical black hole. Additionally, this lab helps to explain rotational motion, also known as centrifugal force, by calculating escape velocity and observing constant orbit in a system. Alright, this is part 1, find the mass of a black hole. All right, so the models here were net force equals sum of all forces, just the idea of universal gravitation, the Fg equals G times big M over little m over R squared times R hat, and also rotational motion. All right, so these were initial conditions of the lab. We had our G constant, the gravitational universal constant, the mass star of the mass, which was 2 times 10 to the power of 30. Delta T was 24 times 60 times 60 in a second. All right, and this is the code here. So we have our initial momentums, our final momentum calculated for the star, as well as our delta, or change in V and change in P. We'll also have our dp dt, which represents F net, as you can see in line 175. We'll also have our P hat calculated, our parallel and perpendicular components calculated for F net, and the change in momentum over time. And also have the magnitude calculated as well. And at the bottom, we also have the code for the arrows for the system, also the scale of the arrows, and that's what you can see on this side over here. Right here, these are the results of the first part. At the calculations, we have the mass of the black hole, which we were trying to find, was 1.41 times 10 to the power of 34 kilograms. Our magnitude of the net force was 9.47 times to the power of 28 newtons. And the parallel and perpendicular components are also calculated as well. The orange arrow in this orbit is, I believe, the F net perp, and the bigger arrow is the F net total. The F net parallel is a small magenta arrow. Because it's smaller, it's kind of hard to see with the yellow circle blocking it, but it's also there. And it's pointing in the parallel direction of the path. All right, so discussion, what does this mean? The net forces components are a little different from the rate of change of momentum, although they were set equal to each other in this lab. Essentially, F net is just force equals M times A for all the forces, which makes it a sum. And the change of momentum is the F net over a mass times delta T. That gives the momentum principle. All right, this is part 2. Don't crash. All right, models here, we have constant orbit, and we're trying to find the escape velocity so that the spaceship can safely clear the planet without crashing into it. These are the initial conditions, right? We have the mass of the planet, the ship, and the black hole as well. We also have the universal gravitational constant, 6.7 times 10 to the power of negative 11. Right, and this is the code for right here. So basically, we calculated the R, like the position between the planet and the black hole, destiny for the ship and the planet as well, and the black hole to the ship, and also to the planet to the ship. We also calculated the R hat for it. We also calculated the force for each, the black hole, the planet, the ship on the planet, the black hole on the ship, and the planet on the ship. Calculate all those F nets. And at the bottom, down line 110, calculate the planet's velocity by using the update velocity formula and planet's position by using the update position formula, which is Newton's second law, and also calculate the ship velocity and ship position as well. All right, these were the results. So right here, the blue line represents the orbit line, and the pink is the ship's path, and the black hole is that black little dot in the middle. The initial ship velocity was negative 3.87 times 10 to the power of 7 in the x component, and 1.5 times to the power of 6 in the y component. Closest black hole was 2.02 times the power 10 to the power of 8 meters before it had to crash by getting sucked into it. All right, so what if the initial velocity for the spaceship needed for it to enter orbit around the black hole can be calculated by doing the following. We're basically using the mv squared over r formula, which equals the universal gravitational formula, and that velocity would be 9.71 times 10 to the power of, I believe, 6 or 7 meters per second. All right, so in conclusion, in short, using Newton's second law and the ideas of universal gravitation, the unknown mass of a black hole as well as the velocity for a spaceship to safely maneuver a planet can effectively be calculated. To improve the precision of this glow script, ensuring vital syntax and correct formulas is super important to keep the program running smoothly. My name is Jim Finney, and thank you for watching my video. Have a good one.